Alright, this is Ken Roosevelt. This is like take 11 or 12. And this is the meager mean and measures of variability. I'm referring to the mean as being meager because even though it does provide some information and that information is valuable, many times we require more to make a well-informed decision, more than the mean. Like, well, the mean isn't enough, the average isn't enough. Yeah, sometimes it's not enough. Look at this example from the book. It's a comparison of outdoor paint. A testing lab wishes to test 2 experimental brands of outdoor paint to see how long each will last before fading. So that's important. The testing lab makes 6 gallons of each paint to test. Since different chemical agents are added to each group and only 6 cans are involved, these 2 groups constitute 2 small populations. So that's important. We're not dealing with samples here. We're dealing with a population. Why? Because these are prototypes. And there's only 6 cans made in the whole world, so they represent the whole of the population. They're not a sample, they are the complete deal. So we have prototype, 6 cans from brand A, 6 cans for brand B. And when you add these up and you take the sum and divide by 6, you get the mean for both is equal. Now, that means that our expectation would appear to be the same with either one. If it's 35 months, we would expect, whether you use brand A or brand B, that we could expect the paint to last an average of 35 months without fading. However, and that's true, that would be a reasonable expectation. However, you would be surprised if you didn't know more information. And that additional information you need to make a well-informed decision about which kind of paint to bring to market is right here in the variability. Now, without making a histogram, it's sometimes hard to measure variation unless you know what I'm about to teach you. So, why do we even care about variation? Well, sometimes consistency is important. We look at brand A and we see that it's not very stable in terms of fade resistance. You had one can last 10 months, another can last 5 years. Brand B doesn't have the longevity that brand A sometimes exhibits. However, we see less dispersion here, and that there's more uniformity, okay, in that everything is more approximate to the mean. It's in the proximity of the mean, where this is a uniform distribution where it's all spread out. You have a 1 in 6 chance that it might last 10 months, 20 months, 30 months, 40 months, 50 months, or 60 months, 5 years. So the question would be, as a business person, which would you rather bring to the market? The one that has a chance of lasting 5 years but may last only 10 months? Or the one that normally lasts between 25 and 45 months? It seems a clear decision to me, but you might think, well, they both have the same average, so what does it matter? Well, let's look first at this right here. This is very important. 25 and 45 months. That's it. Okay? All the cans are within that time frame. Here, 10 and 60. So while it's true their averages are the same, which one could you offer a 24-month warranty on? Not A. You wouldn't want to. You could. Here's 24 months. You would expect that 33% of your customers could seek compensation from you if you use Formula A, because 33% of the time you would expect failure of fade resistance before the 24 months was up. Whereas here, if you gave a 24-month warranty, your experiment here indicates that you would be pretty safe. So you could guarantee this product for 24 months and have a low expectation that you would lose much money paying off warranty claims. So I would go with B. Variation is a big deal, especially when you're talking a manufacturer or medication. You know, you don't want reactions all over the place. You want predictability, and that is what variance, standard deviation are. They're a measurement of predictability. How close to the mean are the other members of the population or the sample if you're doing sample variance, and we'll get to that later. Okay, so you heard me say it, that we're interested in how close do the values approximate to the mean. Before I start breaking that down and try to figure that out, let me give you the first and most basic measure of dispersion, and that would be, well, range. Okay, range is something you start learning about in middle school. It's high minus low. This has a range of 50 months. This has a range of 20 months. Highest value minus lowest value. But it doesn't tell you about the shape. Range doesn't tell you that this is uniformly distributed. Doesn't tell you that this has a little, bump in the center. Doesn't tell you about the symmetry. It just tells you high and low. So you can have a very normal bell-shaped distribution, and you can have a skewed distribution. Both have the same range. You can have something that's bimodal. Range doesn't really tell you a lot. It just tells you high and low, and the difference between them. So we want something more explicit, and we'd actually like something that we could look at as a number that, without having to draw a picture, would give us a good idea of how dispersed the data is without having to histogram it. So we might try to measure the average of the differences between the values and their mean. So the average of the differences. So let's go. The differences between a value and its mean is x, the value, minus the mean. And we could do 10 minus 35, 20 minus 35, 30 minus 35, 40 minus 35. I need to pick up the speed. And we could try to figure out those differences and add them up and take the average. So we're actually thinking about doing this, and we want to see what that comes out to. But when you do it, you run into a problem, because there's a truth about the mean that you might not realize. See, the mean in statistics is synonymous with the fulcrum in physics. It's the center of mass. It's the balancing point. And so when you add these guys up, the sum of the differences will always be 0, because there has to be, for all the negative differences over here, they have to be balanced out by equal number of positive, not equal number, but by equal total of positives over here. And that's not just for a uniform distribution or a symmetric distribution. It's true for all distributions. If I had 4, 6, and 14, by no means is that symmetric. The average would be 8. You'd have 2 to the left, 1 to the right. Pretty spread out. But if you went 4 minus 8, 6 minus 8, and 14 minus 8, you get -2, -4, and +6. And when you add them up, you get 0. The sum of the differences is always going to add up to 0. So we can't use that as a measure of variability. But we're on the right track, and we'll get there in the next video. So that's it for now. Bye.